What's up, everybody? I'm Steve, and today we're covering USACO 2024, December at the bronze level, problem number 1, roundabout rounding. Bessie the cow is back in school. She has started doing her math homework in which she is tasked to round positive integers to powers of 10. That just means to 10 or 100 or 1,000. To round a positive integer, a, to the nearest 10 to the b, where b is a positive integer, 10 to the b just means that it's going to be some power of 10. Bessie first locates the beef digit from the right. Let x denote this digit. For example, let's just do like a random number, 375. The beef digit to the right, which is some power of b. Could be this digit or could be this digit. Let x denote this digit. So for example, if we were to pick this digit, the 3, then x would be equal to 3. If x is greater than or equal to 5, Bessie adds 10 to the b to a. So the beef digit, if this is the third digit from the right, the beef digit from the right, if this number is greater than or equal to 5, she will add 10 to the third, which would be 1,000. Then Bessie sets all the digits, including and to the right of the beef digit to the right, to be 0. 0, 0, 0. Okay, let's run that with a couple numbers. It's actually pretty straightforward if you just do a couple numbers with these. So if I have a number like 546, then this is the first digit to the right, the second digit to the right, the third digit to the right. So then this is x equals 5 in this case, x equals 5. And if this digit here is greater than or equal to 5, then I'm going to add 10 to the third, which would be a 1 here, and set all the rest of the digits to 0. 0, 0, 0. That's how normal rounding is typically done. For instance, if Bessie wanted to round 456 to the nearest 10 to the 2, which is 100, she would locate the second digit from the right. This is so that b equals 2. Check to see if it's greater than or equal to 5. Second digit for the right is 5, which means x equals 5. This means x equals 5. And since x is greater than or equal to 5, she would add 100 to a, which would make this 500, and set the rest of the digits to 0. Having now successfully rounded to the nearest 100, resulting in 500. However, if Bessie were to round 446 to the nearest 10 to the 2, she would end up with 400. Because in this case, the second digit x is equal to 4. The criteria is to round down. Down here now, after looking at Bessie's homework, Elsie thinks she has invented a new type of rounding, chain rounding. To chain round to the nearest 10 to the b, Elsie would first round to the nearest 10 to the 1, then the nearest 10 to the 2, and so on until 10 to the b. She's not going to start at just this digit. She's going to work her way across one digit at a time rounding. So first rounding to the nearest 10, then to the nearest 100, then to the nearest 1,000, and so forth, until she gets to whatever digit we're trying to round to. Bessie thinks Elsie is wrong, but is too busy with math homework to confirm her suspicions. She tasks you to count how many integers, x, how many integers, at least 2, and at most n, where n is between 1 and 10 to the 9th, exist, such that rounding x to the nearest 10 to the p, using Bessie's technique, is different from chain rounding to the nearest 10 to the p, which is Elsie's technique, where p is the smallest integer such that 10 to the p is greater than or equal to x. I want to just do some chain rounding and try to find situations where chain rounding would get the wrong answer. We need a number such that rounding this digit first and then rounding this digit would get a different result than rounding this digit first. So let's say like this is 200. Now we got to think of what can we put here and here where rounding the ones digit first would give us a different end result than simply rounding from this digit first. Situations where we round up naturally would be like 250, anything, 250 up to 299. 250 to 299 all round up. But we want to find a situation where chain rounding is either going to cause us to round up incorrectly or round down incorrectly. Because we're moving our way from right to left, if this is a 5, there's no situation where rounding this down is going to change that from being a 5. So the only thing we can really do is trigger a incorrect roundup. So how are we going to trigger an incorrect roundup? Let's say like this was an 8, and then this digit was something that would cause a rounding down, but after rounding up won't. For example, a 4. Well, 248 is a situation where if you normally round to the nearest 100, because this digit is not greater than or equal to 5, it would round down to 200. But if we use Elsie's technique and round this digit first, which is an 8, that'll round up to 50, And then when she rounds this digit, that'll round the whole thing up to 300. We're going to try and think of what is the range of the numbers where chain rounding is going to break. If I have some number of 100 and this is easy to do with tens first. If I have a 4 here, and then it could be anything over here. If this is a 5 up through a 9, those are all going to round up and cause this 4 to become a 5, which then when I round this digit, that'll cause an incorrect round. So what about 3-digit numbers? What are those going to look like? This needs to be a situation where it causes a waterfall effect. And the core of the chain rounding is the ones digit being 5, 6, 7, 8, or 9, causing a roundup that causes this digit to round up incorrectly, which means this has to be a 4. Because if that's a 5, it's already going to round up. And if it's a 3, it's not going to round up even after being rounded up to 4. So then what digit could we put here that will cause a waterfall effect? Well, if this rounding up to a 5 causes this to round up, and we want to go even further, this also has to be a 4. Because then when this rounds up and makes this a 5, that'll round up and make this a 5, which will round up and potentially make that a 5 if that's a 4 as well. Let's look at that 10 to the p situation, because that also is an important thing for how we're going to round it. They're not going to give you p in the problem input. You have to calculate p such that p is the smallest such number where 10 to the p is greater than x. So if p was like, let's use one of these examples, 4, 5, 6, 7. Then what does p need to be? We need to have a p such that 10 to the p is greater than x. In order for it to be greater than x, the result of 10 to the p, in this case, has to be here. And that's the digit we're rounding to. We're always rounding to one digit further than whatever the number is. And that's provided. We're not ever going to round to something arbitrary in the middle. If I round this according to Bessie's method to 10 to the p, which is 10,000, I'm going to end up with 0. And if I round it according to Elsie's method, then this 7 is going to round up, this 6 is going to round up, the 5 is going to round up, this will become a 5, which will round up, and it'll become 10,000. Okay, let's check the input format. You have to answer multiple test cases. I have a good way to approach this as well. We'll get to that in the coding section. The first line of input contains a single integer t, where t is between 1 and 10 to the 5th. That's how many numbers you're going to have to solve. This actually is important too, because this 10 to the 5th means we're not going to be able to actually run this as a simulation. 10 to the 5th is too many test cases. And then if we have numbers that go up to 10 to the 9th, we obviously cannot brute force this. The problem is that for each of those numbers, once we get up to like the 9-digit numbers, if I have like 9, 5, 3, 4, 2, 6, 273, chain rounding through those 9 digits for every single number is going to be a problem. We're going to have to use math to solve. All right, so here we go in the visualization. I was trying to figure out a good way to represent this one in a tactile way. I had an abacus. I was giving that a try for like 45, for example. We could do like 4 and then 5, something like that. And then the 5 rounds down and the 4 rounds up. But I feel like the pips are just easier, so we're going to stick with that. What you're seeing here represents 4,567. So when it's time to do rounding, we're always rounding to the nearest whatever the place is past the end of this. So with conventional rounding, if I were to round to this digit, since this is a 4, this whole thing rounds down and it becomes 0. But if this was a 5, regardless of what's over here, this whole thing rounds up and this would become a 1 followed by all zeros. What happens with roundabout rounding is we start over here and we round. I need a good placeholder for a 0. I'm going to use these characters to represent zeros. So right now this is a 7. If I round up, for example, if this represents just, if I take this out and this just represents 67, then what I would do is I'm going to round this and put this guy here to represent a 0 and then carry the 1. And now this is a 7. I'll round that and put Bessie here to represent a 0 and carry the 1. And I'm left with 100, 100. When rounding 4,567, 4, 5, 6, 7, with roundabout rounding, we always start in the ones digit. And if this is 5 or more, we round it up. So it is. So we'll carry the 1 and make that a 0. Because this is more than 5, we'll carry the 1 and make that a 0. Because this is more than 5, we'll carry the 1 and make that a 0. And because this is now 5 or greater, we'll carry the 1 and make that a 0. And we're left with 10000. Regular rounding with a 4 here would have rounded down. Roundabout rounding rounds up. What we need to do to solve this is not brute force this, because we know there's too many to brute force. We need to kind of play around and think about what rounds up and what rounds down. So let's start with like 29. So if I had 29 and I do roundabout rounding, I'm going to round up, but then this is going to round down and I'll end up with 0. Same as conventional rounding. Because remember, we're always rounding to the digit here, which would be the nearest 100. What's the first number that's going to round up to 100 incorrectly on roundabout rounding? Well, it's probably not something with a 9, because 9 rounds up the same way that 8 does, the same way that 7 does, the same way that 6 does, and the same way that 5 does. But the 4 would round down. So our smallest number that's going to round up is going to be a 5 here. Now, if this is a 5 and we carry 1 over, in order to round up, this has to become 5. after carrying. If this is going to become 5 after carrying, it starts at 4. And that kind of gives us our basic number. 45 is the first number such that when you round this up and carry the 1, make that a 0, and then round this up by carrying the 1 and make that a 0, you get 100. Even though we know that 45 should not be getting rounded up. You'll never stop me. When I go back to 45, 45 is going to round incorrectly. And actually, everything between 45 and 50 will round incorrectly. So 45, 46, 47, 48, and 49 will all round incorrectly because 49 should round down. But just like 45, 49 will carry the 1, and you'll end up with 100. We can count those up. 45, 46, 47, 48, 49. We've got 5 numbers that are going to erroneously round up. After which we're at 50. 50 will round up regardless of which method you use because the 0 here won't do anything. And then the 5 would carry the 1 and round up. And then you've got 100 again. 3-digit numbers have a similar principle. Remember, we're going to need a 5 here because we want to kind of create this chain reaction. We want to figure out the smallest such number that's going to incorrectly round up. And if we're starting with, like, for example, 300, I'm going to put a 3 here. Let's do 315, for example. Just start low. And so we want numbers that'll round up to 1,000. In order to round up to 1,000, working backwards, we have to have a 4 here so that when we carry the 1, it'll incorrectly round up. In order to carry the 1, we have to have a 4 here so that it'll incorrectly round up. And we could have a 5 here, but it doesn't need to have a 5 here. That would be a higher number that'd work, but we want the lowest such number that works. 445 is the lowest such number that'll work, because what's going to happen is we have this chain reaction. If I had 444 and I use chain rounding, this rounds down, that rounds down, that rounds down, and I end up at 0. Once I get to 445, which is my lowest such number, the 5 will round up and carry the 1, and I get a 0 and a 5, round up and carry the 1, round up and carry the 1, and I'm left with 1,000. From the number 445, 445 will round up incorrectly. So will 446, 447, 448, 449, 450, 451 still rounds up because even though this will round down, the 5 will round up. Once we get a 5 here, we're already committed to that roundabout rounding process. 450, 460, 470, 480, 490, up to the highest number being 499. 499 is the highest such number that'll round up. If I have 499 as my largest number that'll round up incorrectly, because 499 after that it's 500 and then they both round up, but 499 will round up incorrectly. I need the number of numbers between 445 and 499, including 499. And if you do the math on that, you'll have 499 minus 455, but then you have to do a plus 1 because of the 499, because the 499 also is one of the numbers that rounds up. This is a weird thing in counting, and I think I mentioned it when I was reading the instructions, but if I want to count the numbers 5, 6, 7, 8, 9, I can't do 9 minus 5 because that gives me 4, but 5, 6, 7, 8, and 9 are in fact 5 numbers. I have 55 numbers between 445 and 499 that round up, and we can continue that process. If I have 4,445, then again, it's going to carry over, and then we'll have a 1. From 4,445 to 4,999, we're going to have 555. And then from 44,445 to 50,000, we're going to have 5,555. This gives you the advantage that you can jump. If you know, for example, that your N number, your target number is like 10,000, from 1 to 10, there's nothing. They all work the same. From 10 to 100, you're going to have 5 numbers, 45, 46, 47, 48, 49. From 100 to 1,000, you're going to have 55 numbers, 445, 446, 447, 448, 449, 450, 451, 52, 53, 54, up to 499. From 4,444 to 5,000, you're going to have 555 numbers. And this pattern is going to continue on up. So when you're looking for a large N, like a billion, for example, do them in chunks of multiples of 10. We can get from 10 to 100 by adding 5. We can get from 100 to 1,000 by adding 55. So really what a lot of this is just managing those numbers. The way I ended up doing this is I had 2 sets of 5. I want to know how many numbers there are between those. When I advance to the next number, starting with 5 and 5, then what I did was I just multiplied by 10. So I'm going to multiply by 10, so it becomes 50. For the lower number, I subtract 1, multiply it by 10, and then add 5, which gives me 45. From 50 to 45 is going to be 5 numbers. With this one, again, I just multiply by 10 to make it 500. With this one, I subtract 1 to make it 44. Multiply by 10, and I add 5 to make it 445. And I can keep doing that. With this one, I multiply by 10. With this one, I subtract 1, multiply by 10, and add 5. And then every step of the way, all I need to do to know how many numbers there are is just subtract those. 5,000 minus 4,445 gives you 555. And then this 555 adds to the total. Keep repeating that until this number becomes too large. Remember one of the test cases was 4, 5, 6, 7. We shouldn't count the numbers between 4,567 and 5,000. If I have 4, 4, 4, 5, and I know that my upper number is 4, 5, 6, 7, then once I reach that top area, I don't subtract 5,000 minus 4,445. What I do is I realize this has exceeded my n. 5,000 is bigger than my n in the case of 4,567. So I set this equal to 4,567. 567. And now all I need to do is I need to figure out how many numbers are there between 4,567 and 4,445, including the 4,567. Easiest way to do that is to add 1 and then just do subtraction. Take away 5. 1, 2, 3, 4, 5 leaves 3. Take away 4. 1, 2, 3, 4 leaves 2. Take away 4. Take away 4, and I have 123 numbers. If you've been doing the math, I have 5 from 45 to 100, and I have 55 from 100 to 1,000. And now between 1,000 and 4,567, I have 123 left. And if I add 60 to that, I have 6, and then this will just be a 0. My sum of those two numbers, 3 plus 0 is going to be 3, 2 plus 6 is going to be 8, and 1 plus 0 is 1, and I've got 183. And 183 is the correct answer for the 4567. In the one that was kind of a weird number, I had a 3,366 to kind of walk through the process. When I'm at 445 versus 500, 500 minus 445, that gave me the 55, brings me up to 60 total. When I multiply this by 10, slide that all over. With the 445, I subtract 1, multiply it by 10, and then add 5 back in. I realize that has exceeded my upper limit. So I replace my upper limit with n plus 1, which would be 3,367. And then I just got to make sure that if I do 3,367 and I subtract 4,445, because that's a negative number, I don't subtract from my solution, which means we add 0 and then the end result is just 60. If we want to be able to solve for large numbers, for example, 10 to the 9th is the biggest number, let's do that, 1 to a billion. From 1 to 10, there's no numbers. From 10 to 100, there's 5. From 100 to 1,000, there's 55. And that pattern continues all the way up. And then here's where things are going to get a little dangerous. Because remember, we need to find the number such that it's greater than or equal to n. Our upper number is going to go from 100 mil to 1 bill. And then from 1 bill, 10 bill is where our while loop is going to cut off. Now this is a problem because 10 billion, if you're in Java or C++, is too big. It's bigger than integers. We're going to need to use a long, or we need to have some sort of a cutoff that realizes when n is equal to exactly 1 billion, we don't keep multiplying by 10 because that will cause an overflow. If you're in Python, you don't have to worry about that. For Java or C++, you definitely have to take that into consideration. You could even hard code this if you wanted to. You could pre-calculate that if the number is less than 100, you do plus 5. If the number is less than 1,000, you do plus 55. You could code every window as having a set number, and that doesn't violate any of the rules. And I've seen that in official solutions in the past. However, I think it's more fun to just simulate it because then you can see the whole process building up, and then potentially it can go to numbers even larger than 10 to the 9th. All right, let's write the code. So we are on to roundabout rounding. Let's just jump in and get started. Include IOStream, namespace, standard, main, return 0. Now this one has multiple test cases. I have a recommendation for that since we have to start in main. I always like to read in the t first, and then for I is less than t I plus plus. I just call a solve method, and then solve is a void method, and then I just treat this like my main. Some people will actually, I've seen, call this just underscore main. I rather call it solve. But now inside of solve, I only have to deal with one test case at a time. So we're going to read in n, cnn, cout case n. Quick sanity check to make sure that's saved in the right place. Make rounda. It's waiting for input. Let's grab the input. All right. And just make sure it's reading all the input. Yep, case 1, 100, 4, 5, 6, 7, and 366. So I mentioned before, we could kind of hard code powers of 10. Like I could create an array where it's like int nums equals 555, 555, and save myself a little computation. I don't really need to do that. So the way we're going to do this is we're going to build around our core number, which is going to start at 5, and we're going to have base, which is going to be 5. The core number is going to keep getting multiplied by 5, so this is one that'll go 5, 50, 500, 5,000, 50,000, and so forth. The base number is always going to be doing minus 1 times 10 plus 5, minus 1 times 10 plus 5, minus 1 times 10 plus 5. As we build these numbers up, we are looking for the core numbers to start approaching 1 billion. We don't actually need to keep track of that 10p thing. All we really need to do is to keep going until our core number becomes bigger than our target number. Remember, n is our target number. So we're going to keep multiplying this core until it exceeds the target. If the number we're trying to solve was like 800 million and we stop at 500 million, that's fine, because there's not any numbers between 500 million and 800 million. There's no numbers at all above 500 million, because from 500 million to a billion, there's no numbers, and we don't go above a billion. So we're basically looking for the core number to reach 500 million, and then we stop. Unless the core number exceeds n, in which case, remember, then we're going to scale the core number down to n plus 1, and then subtract that minus the base number. I'm starting these both at 5 just to kind of prime it, but actually, right as soon as my while loop gets going, I'm going to immediately be doing core equals core times 10, and then base equals base minus 1 times 10 plus 5. And let's just look at how those numbers compare. We're going to run this while the core number is less than n. Because as long as the core number is less than n, I have numbers left to go. Once the core number reaches n, I have to stop. So we have these numbers here, and then I'm just going to do cout the core number and the base number, so we can kind of see what that process looks like. We're going to make rounda, dot slash rounda, 4, 1, 100. There we go. So I got 45 to 50, and then 445 to 500. The base number is where we're starting, and we're going up to the core, which is like the core of the, I don't know why I called it core, but let's run with it. Let's do 4, 5, 6, 7, just because we already looked at that. For 4, 5, 6, 7, I'm going to have 50, 500, 5,000, and then, again, we'll have the difference between 45 to 50, 445 to 500, and then 445 to 4567 plus 1. If I have a big number, 1, 2, 3, 4, 5, 6, 7, 8, 9, then those are all the numbers I'm going to have. Now remember, I was talking about we got to be careful about an overflow. That's exactly what happened here. This got to 500 million, which was less than a billion, then it multiplied by 10. But what happens when you multiply 500 million by 10 is you get 5 billion, which wraps around. So we ended up with like 700 million, and then we ended up with a negative number. So we're going to have a catch in here. And the catch is going to be that after ending the loop, before we loop around, if our core number is equal to 500 million, then we're going to have to break out. We do need to check to see if our core number is greater than n. And if that's the case, we're going to set the core number equal to n plus 1. After scaling that down, remember we had that case where we have 3,366. If our core number, as a result of scaling to n plus 1, is now less than our base number, which is the 4445, then we have to exit immediately because there's nothing to add. We don't want to put a negative number in. But if we get down here, the implication then is that our core number, either the 5,000 or whatever the 4567 is, or whatever the number is we're going to be subtracting 4445 out of, is greater than it. And if it's greater than it, then we can add that to our result. We need a result variable. Let's call it count. Int count equals 0. Once we get down here, count plus equals core number minus the base number. I'm going to change this to times equals, just to make that a little cleaner. Times equals 10, and then base minus 1 times 10 plus 5. Okay, that looks good. And then that'll count in. Let's see, base and count. Oops, count. I want to see the base number and the count number as they go up. And then finally, we're going to report the count at the end. That's a void function, so we don't have to return anything. Let's make rounda. This time I'm going to paste my input in. All right, let's see. 4, 5, 6, 7, 3, 3, 6, 6, and 0. Okay, so the 0 goes to the 1, because 1 has nothing. For 100, we got to 45. The base number is 445. And 101 is definitely less than 445, so we broke out and reported the count, and that's where our count of 5 got reported. Same thing happened to the 45 added 5. It's outputting it on the next loop. The 445 added another 5, which brought it to 60. And then the next number would have been 5,000 for the base. 5,000 is more than 4,567, so it scaled it down to 4,567 plus 1, which is 4,568. We got 4,568 minus 4,445, which is 1, 2, 3 added in. That brought us up to 183. We exited and printed out the count. So this is all working the way that we explained it in the algorithm, and it looks like it's working correctly. I'm going to go ahead and double check it one more time with a large number. Make rounda clear round 1 case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 61, 7, 2, 8. I think I checked that before, and that is in fact what it should be. All right, let's go ahead and submit it. CPP. All right, let's move on to the Java. Import Java util scanner, class rounda, static void main, string args, int t equals sc next int. All right, scanner sc equals new scanner system in. One thing that's weird is we're gonna see this in a minute. For int I equals 0, I less than ti plus plus. We're gonna call that solve method. If I don't pass the scanner to solve, public static void solve, and I create a new scanner here, c equals new scanner system, and we'll do int n equals sc next int, and then we're just gonna system out print line, and watch what happens when I do this. I'm gonna do java c rounda.java, java rounda, grab my test cases and paste this in all at once. So what happened there? Reason why, when I opened the new scanner, it didn't take the rest of this stuff. The first scanner is waiting for this stuff. And actually I can demonstrate that. System out println sc.nextInt. We're gonna call that 4 times at the end. This is some really weird quirky behavior with the scanner, but each scanner, despite the fact they're both scanning the command line, if I paste everything as a blob, that all is dedicated to this scanner right here whenever I decide to take from it. Make that again. Oops. Java C rounda Java, Java rounda. Grab this stuff, paste. See? So then I'll do 3, 4, 5, 6. And then now look, that other stuff came out at the bottom here. In order to prevent them from happening, we're just gonna pass the scanner to solve. Scanner, SC. The short piece of, I guess the short way of stating that is, when you do this separate test case thing, don't open a different scanner. Just pass your scanner and just pass it every time you need it. And that'll allow you to then correctly be able to paste in your code here, your test case here, and it'll catch all of them. We're gonna have core equals 5, base equals 5, count equals 0. And just to kind of remind you how we're gonna do this, we're gonna count up to n. And every time we do that, I'm gonna make my core numbers be something like 5, 0, 0, 0, and my base be something like 4, 4, 4, 5. This wasn't a great choice of terms, core. I keep forgetting what that means. I chose that to core because that's the middle of the 10p thing, and that's the foundation at which I am getting the difference between the base and that core number. But every time I read core, I forget what it's about. So while core is less than n, while core is less than n, we're gonna do core times equals 10, and base equals base minus 1 times 10 plus 5. So, again, minus 1, we'll drop that down to 4, 4, 4, 4. Times 10, we'll make it 4, 4, 4, 0, and then plus 5, we'll go like that. And then for the core, we're just gonna keep multiplying it by 10. So that'll just be basically the equivalent of adding a 4 on the left side of the base number and adding a 0 on the right side of the core number. Once I have that, I need to check to see whether or not my core number has exceeded n. If core is greater than n, I might have something like 4, 5, 6, 7, but my core number is now at 5,000. I don't want the difference between 5,000 and 4, 4, 4, 5. I want the difference between 4, 5, 6, 7 and 4, 4, 4, 5. So if that's the case, I'm going to reset my core number to become n plus 1. However, in the case of 3366, if that has happened, and I set my core number to 3366 and my base number is 4445, if I do 3366 minus 4445, there aren't any numbers between those. So if my core number is now less than my base, which is the 4445 number, then we're going to break, because then there's no numbers between those two. Finally, the count is going to go up by the difference between core minus base, and if my core number has reached 500 million, then I want to break out, because otherwise I'm going to loop back around and multiply it by 10. It's going to hit 5 billion in overflow, and that'll be a mess. Well, it won't be a mess. It'll just either be an infinite loop or it'll give us the wrong answer. System out println the count. Java C, rounda.java, Java rounda. We're just going to test it with the test file here, paste. Okay, and then 0, 5, 183, 60. I think we're good. I'm gonna go ahead and just test it around with 1 billion. Yeah, nothing funny seems to have happened for that. So we're gonna go ahead and submit. Pick out Java, choose file, Roundabout Java, open and submit. Okay, that's looking pretty good. Okay, finally we're gonna tackle it in Python. I'm gonna grab my sample data before I move over. I always like to paste the sample data at the top. It just kind of helps keep me on track. Okay, first thing we're gonna have to do is read T for test case. T equals int input. And then for I in range T, I'm just gonna call a solve method. I'm gonna kind of keep that same pattern. N equals int input, core equals 5, base equals 5, while my core number is less than n, basically working our way up towards n with this 5 number. And in case you skip to the Python, this is going to be the 5 with the zeros building. This is going to be the 4445. And the way I'm going to get to the next set of these, I'm going to core times equals 10, which will just basically add a 0 on, and base equals base minus 1 times 10 plus 5. Let's look what's going to happen. So minus 1, boop, times 10, boop, plus 5, boop. So that'll basically be like adding a 4 to the left. That's the quickest way to do that. Now there's two things I need to check for. The first is if my core number, which is this 5000, has become larger than n. If that's happened, then that's going to be a situation like here, where I've gotten up to 5,000. Remember, the goal is every time I iterate, I'm finding the difference between these two. So for example, with 4, 5, 6, 7, I start with 45 and 50. The difference between these is going to be 5 numbers. So that's 5 numbers in that range. But we have to go further. So we go 500 and then 4, 4, 4, 5. We still have to get up to 4, 5, 6, 7. So the difference between these is going to be 55. We're going to add that to the total. Boop, boop. So now we're at the situation where I don't want to add the difference between 5,000 and 4, 4, 4, 5 because 4, 5, 6, 7 is my upper number. In order to find out how many numbers there are between and including 4, 4, 4, 5 and 4, 5, 6, 7, I'm going to set my core number as equal to n plus 1 for the subtraction. That way I can do 4, 5, 6, 7 and then 4, 5, 6, 8 minus 4, 4, 4, 5 and find out how many numbers there are, and then I'll break out and return the solution. However, if as a result of this n plus 1, I ended up with something like 3, 3, 6, 7, I don't want to add 3, 3, 6, 7 minus 4, 4, 4, 5 because there aren't any numbers between that. So if my core now has become less than my base number, which is the one with all the 4s, then I'm going to break out of the loop. Finally, if I get down here, my count, I've got to create count equals 0, has to go up by my core minus my base, and then I don't actually have to do anything with breaking here. There was an issue with the Java and the C++ with going over int max. I don't have to worry about that with Python. So what's going to end up happening, let's just run it and see. Actually, I don't think I have to do any handling for that at all. We're going to do print count. Let's just see real quick. Let's just see real quick if that works out the way I think it will. Python 3 round.py. It does seem to have worked. All right, let's just submit it to the site and see what happens. Python 3, choose file, round.py, submit. All right, that was easier than expected. And again, I had to do a break in the Java and the C++. I'll just go ahead and show you real quick. After doing the count plus equals core times base, in both the Java and the C++, I had to check to make sure if I was at 500 million, because we can't go up to 5 billion unless we switch from an int to a long. Python, we don't have to worry about that though. So what's going to happen is the core would be multiplied by 10, the base would become whatever, and if the number gets too big, like above int max, and I end up with 5 billion, 4.444 billion to 5 billion, that would have been way more than any n they could give because the upper n was 1 billion. And then by making it n plus 1, 1 billion would have definitely been less than 4 billion, and it would have broken its own prior to adding. So we didn't have to do that extra catch in the Python. Alrighty, that's roundabout rounding. It's in all 3 languages. Hopefully that was helpful for you, and I'll talk to you in the next video. The beef digit from the right, beef digit from the right, the beef digit from the right, beef digit from the right. The beef digit from the right. Beef digit from the right.